Hello everybody, welcome to this next video on linear algebra. In the last video we saw that t from v to v is diagonalizable if and only if it has n eigenvalues. So n is the dimension of the space, so they may be repeated such that for each eigenvalue am is equal to gm. So this is a test now we have for checking whether a given linear operator is diagonalizable or not. So we are going to do this test here. So let us look at the first example. We will take 2-3 examples to use this theorem. We'll see how we can use it. So let us look at the first example. Find the algebraic and geometric multiplicities of the eigenvalues of the matrix You see, if a result is true for, we are saying this is for an operator, then it is equivalent to saying that it is for a matrix, because anyway for operator we convert it into a matrix first and then we check the conditions. A is equal to 3, 7, 6, minus 1, minus 5, minus 6, 1, 1, 2. Right. Further check if it is diagonalizable. Fine. So let us do it. So what you will do, you will write determinant of a minus lambda I. That will be determinant of 3 minus lambda, minus 5 minus lambda, 2 minus lambda, 7, 6, minus 6, minus 1, 1, 1. Right. So you find out this will be lambda cube minus 12 lambda plus 16. And you can see that by trial, you can see that lambda is equal to 2 is 8 minus 24 plus 16 is 0. Therefore, it is a root. So this is, if you factorize, you will get lambda minus 2 square into lambda plus 4. So your characteristic equation is, this is your characteristic polynomial. So your characteristic equation looks like, is lambda minus 2 square, lambda plus 4 equal to 0. So lambda is 2 comma 2 comma minus 4. So you have eigenvalues are 2 and minus 4, and this 2 is an eigenvalue 2 times. Therefore algebraic multiplicity, which is defined as number of times an eigenvalue is a root of the characteristic equation. So here the eigenvalue 2 is repeated 2 times, that is why its algebraic multiplicity is 2, and eigenvalue minus 4 is repeated 1 time, so its algebraic multiplicity is 1. Right. Now to check if the matrix is diagonalizable or not, we need to compute the geometric multiplicities. Geometric multiplicities are the dimension of the eigenspace corresponding to the eigenvector. So for lambda is equal to 2, to compute eigenvectors, we need to find the solution of this system A minus 2i x, y, z, because we have 3 cross 3 matrix is equal to 0, 0, 0. You just put it, you will get 1 minus 1, 1, 7 minus 7, 1, right? And then you have 6 minus 6, 0. Then you have x, y, z equal to 0, 0, 0. This is the system you will get. Now you can just do some modifications. R2 goes to R2 minus 7 times R1, and R3 goes to R3 minus 6 times R1. So you will get 0, 0, minus 6, 0, 0, minus 6, 1 minus 1, 1. X, y, z is equal to 0, 0, 0. So you will get z is equal to 0, x minus y plus z is equal to 0, which implies x is equal to y. So your eigenvector looks like x, y, z is equal to x, y is x, z is 0. So this is x, 1, 1, 0. X belongs to R. So geometric multiplicity is, this is a vector space, subspace with dimension 1, because you can see that there is one element generating it, that is linearly independent. Dimension is 1. Fine. Therefore, geometric multiplicity of 2 is geometric multiplicity of 2 is 1 and its algebraic multiplicity is 2. Therefore, it is not diagonalizable matrix. It is not diagonalizable. Fine, but because we are asked the geometrical multiplicity for each, therefore we can compute it for lambda is equal to 4 also. But if your question is just check for diagonalization, then you can stop here. So for lambda is equal to 4, eigenvectors, to compute eigenvectors, what you will do, you'll have lambda is equal to minus 4, I'm sorry. So you will have a plus 4I x y z is equal to 0, and you make sure this thing, that the moment you see this thing, that the algebraic multiplicity is 2 and 1, you are sure that geometric multiplicity here will be less than equal to 2 and here it will be less than equal to 1, because we have algebraic multiplicity greater than equal to geometric multiplicity. This result we already have. So you cannot have here you cannot have 2 as the geometric multiplicity of minus 4. So you can have at most 1. You will have 1 for sure. So you will have 7, 6, minus 1, minus 1, minus 6, 1, 1, 1. So even if you have algebraic multiplicity 1, you don't need to compute the geometric multiplicity. It will be 1 always, because it cannot be there, because whenever we have one eigenvector, all the multiples of that eigenvector are the eigenvectors again. And if you get minus 4 as your eigenvalue, then for sure there is an eigenvector, right? So here this is the matrix you will get. So you just do it. So you see this one and this one, they are same. So you will get 7x minus y plus z is equal to 0. 6x minus 6y plus z is equal to 0. So you get from here x is equal to 0 and y is equal to z. X is equal to 0 and y is equal to z. So your eigenvector looks like x, y, z is equal to x is 0, y is z, z is z. So this is z into 0, 1, 1. Z belongs to R. So this is your space with dimension 1. Therefore, geometric multiplicity is 1 for minus 4. Right? And these 1, 1 here, 1, 1, 0, and this 0, 1, 1. These are the two linearly independent eigenvectors. Okay. Now let us look at one more example. Question is, let t from r cube to r cube be defined by t of x, y, z is equal to 2x plus y minus 2z, 2x plus 3y minus 4z, x plus y minus z. Suppose this is the map defined. Find all the eigenvalues of t. Find all the eigenvalues of t. And find a basis of each eigenspace. And find a basis of each eigenspace Is T diagonalizable? If so, find the basis of R cube. That diagonalizes T. And find its diagonal representation D. Right, so let us do it. So you have this map here. Fine. T of x, y, z is equal to 2x plus y minus 2z, 2x plus 3y minus 4z, x plus y minus z. So you have to find all the eigenvalues of T and basis for each eigenspace. Okay, so the first thing which we have to do is we have to find a matrix representation of this T. So step 1 is find matrix representation of T. Right, that we do with respect to standard basis. So you can do that with respect to standard basis. What you will do, you will take a standard basis E1 which is 1 0 0, then you have E2 which is 0 1 0, and then you have E3 which is 0 0 1. Right, now T of E1 is T of 1 0 0, that will be 2 2 1, so that is 2E1 plus 2E2 plus E3. Then T of E2 which is T of 0 1 0, that will be, you just put it here, 1 3 1 1 3 1. You see, you put in this formula 0 1 0, so y is 1, so you'll get 1 3 minus 1 3 1. Right, so this is your 1E1 plus 3E2 plus E3, and then T of E3 is T0 0 1. Okay, then this is, you put it here, so you have minus 2 minus 4 minus 1, minus 2 minus 4 minus 1, so this is equal to minus 2E1 minus 4E2 minus E3. Fine. Now your matrix representation of T, this will be your first column, and then this is your second column, this is your third column. Right, so your matrix representation of T with respect to standard basis will be 2 2 1 1 3 1 minus 2 minus 4 minus 1. So with respect to this we will find the eigenvalues. So it is immaterial that which basis you choose. So you can choose any basis here. I have taken standard basis just for the simple calculations, but we have proved that the characteristic equation is independent of the basis you choose here. Right, because the matrices are similar and similar matrices have same characteristic polynomials. Right, so you can choose any basis. So this is your matrix representation. Now you can find the eigenvalues. Eigenvalues you can find. For that, what you will do, call it A. So you have determinant of A minus lambda I equal to 0. So you get 2 minus lambda, 3 minus lambda, minus 1 minus lambda, and here you have 1 minus 2 minus 4, 2 1 1. Right, and its determinant you want to make it equal to 0. Right, so you do it, you'll get lambda cube minus 4 lambda square plus 5 lambda minus 2 equal to 0. So this is lambda minus 1 square, lambda minus 2 equal to 0. So you'll get lambda is equal to 1 1 2, lambda is equal to 1 1 2. Fine, so you get two eigenvalues 1 and 2. 1 is repeated 2 times, therefore algebraic multiplicity of 1 is 2, and 2 is occurring as a root of characteristic equation only once, therefore the algebraic multiplicity of 2 is 1. So algebraic multiplicity of 1 is 2 and algebraic multiplicity of 2 is 1. Now let us find the geometric multiplicity. For that we have to find the eigenspaces. So for lambda is equal to 1, you have to solve A minus 1i xyz equal to 0 0 0. So that will give you 1 1 minus 2. Please do the calculations yourself. Right, then only you will understand the things. You can just pause the video and you can do the calculations yourself, and then later on you can match it. Right, so you have 0 0 0 here. So these are, you see, these are the same equation here, here, here. The second equation is just a multiple. So you get x plus y minus 2z is equal to 0. So you get z is equal to x plus y by 2. Right, so your eigenvector looks like x y z is equal to x y z is equal to x, y is y. There are two free variables because we get only one equation, right? So x plus y by 2. So this is x 0 x by 2 plus 0 y by 2. I can write it as x into 1 0 half plus y into 0 1 half, where x and y are real numbers. So now this is a space with dimension 2 because these two are the linearly independent vectors spanning your space. So this space has dimension 2. This space has dimension 2. Therefore, geometric multiplicity of eigenvector lambda is equal to 1 is 2, which is equal to its algebraic multiplicity. And these are the two linearly independent vectors. Save it, we'll use it later. Now, the another eigenvector value is lambda is equal to 2. So, you need to solve A minus 2i x, y, z is equal to 0, 0, 0. Fine, you do it. What you will get? You will get 0. You'll get 0, 1 minus 2, 2, 1 minus 4, Then you have 1, 1 minus 3. Again, I'll ask you to do the calculations yourself. X, Y, Z, 0, 0, 0. So here you'll get y minus 2z equal to 0. And then you have 2x plus y minus 4z equal to 0. And x plus y minus 3z is equal to 0. Right, now you have to manipulate it. I'm just multiplying this equation with 2. So you'll get 2x plus 2y minus 6z is equal to 0. Now I am subtracting these two. Right, subtract these two. So you'll get, you'll get minus y plus 2z equal to 0. So you get this first equation. Right, so you get y is equal to 2z. Right, so first equation is basically coming from these two. Now you can use any of these two. Let us use it again. So you have x plus y minus 3z is equal to 0 and y is 2z. X plus 2z minus 3z is equal to 0. So you get x is equal to z. So you get x is equal to z, y is equal to 2z. So your eigenvector x, y, z looks like z, y is 2z, z is z. So that is z 1 2 1, right, where z is any real number. So this is the eigenspace of lambda is equal to 2. And what is the dimension? It is generated by single element, and that single element being non-zero is linearly independent. So its dimension is 1. Therefore, geometric multiplicity of lambda is equal to 2 is 1, which is equal to its algebraic multiplicity. So we get that. For each eigenvalue, algebraic multiplicity is equal to geometric multiplicity. Therefore, T is diagonalizable. Fine. Now let us find out the basis with respect to which it has a diagonal representation. Now we know that these linearly independent eigenvectors, you get 3 linearly independent eigenvectors, 1, 2 and 3. These form a basis. So you make a basis beta where your first element will be this 1 0 half, second will be 0 1 half. So your first element is 1 0 half, another is 0 1 half, and then the third element is 1 2 1, right? So this is the required basis with respect to which T beta beta is diagonal. And you don't have to compute it, you just write. Now the first column is corresponding to eigenvalue 1. Second column vector, this element of the basis is corresponding to 1. And third is corresponding to 2. The same sequence you will get here. Right? If suppose instead of this you write like this, you can write, obviously there is no condition, you can write 1 2 1 here, 1 0 half, and then 0 1 half. Right? Then this corresponding to 2, this is for 1, this is for 1. So you'll get 2 1 1. So it is like this. So you don't have to actually compute the representation again, although you can do that, but there is no need. You can straight away write this diagonal representation. It will be just the eigenvalues of that matrix. Right? Now you see that it is not required that the eigenvalues are distinct for matrix to be diagonalizable. The only thing which we need is AM should be equal to GM. Okay. So thank you for watching this video. In this video we talked about the diagonalization of a simple matrix or a simple linear operator without any condition. Next video we'll talk about when your matrix has a special property of being real symmetric, and there we will see that we have interesting things occurring. Okay, so please do subscribe to this YouTube channel and please share